Hi everyone. I hope you got enough time to try the problems. So the first problem is a computational one. This has a Bashi solution by casework, but the reason I put it in is because it has a beautiful solution using graph theory. Okay, so have people solved it? Never mind. Anyways, so okay, so first of all, many of you won't know what arrows means. Arrows is basically a fancy term for just having a bunch of objects and relating one with the other using an arrow. It's just a tool to help visualize things and to make things easier, to give the problem some sort of structure when it's difficult to do so. This, and then you can maybe check if the problem, if the structure in the problem has a triangle or not, has a cycle or not, has if it has a cycle, how many edges are connected to it. I mean, suppose this is a cycle, then can a vertex be connected to a cycle without being a part of another cycle? I mean, stuff like that. And I mean, you can check the degree of each vertex. This can be used in many ways, as we are about to see. So the problem says to find functions from 1 to 5 to 1 to 5 that satisfy f of x equals. Okay, so one thing common in these type of questions, whenever I mean, arrows involves questions with many f's. This is a strong hint to use arrows. Because you can just map an element to its image by an arrow. Suppose if 1 equals 2, then I draw an arrow from 1 to 2. Suppose f of 2 equals 5, I draw an arrow from 2 to 5. And let's take an example function. F of 1 equals 2, f of 2 equals 5, f of 3 equals 3, f of 4 also equals 3, and f of 5 equals 4. Okay, so this goes to itself. This goes. Okay, so this is the arrowed version of this function. Is that okay? Okay. Yes. So now what we want to see is you pick an element, go along 2 arrows. That's the same as you pick the same element and go along 3 arrows. That is the after the second arrow, it maps to itself. The function maps to itself. Okay, so the first question I want to ask you guys is, can okay, yeah, can there be a path? What is the maximum length of a path there can be in this function? 2. Yeah, right. You can see it here, because if there is a path of length 3, then suppose this is x, then f of x is this thing, whereas f of f3 of x is this thing, and they are not clearly not equal. So after the second arrow, if there is an arrow, by arrow I don't refer to self loops as in here, as in here. So if there is an arrow, f of x and f of x are different, and that cannot be. So the maximum length of path is 2. Uh, Also, can there be any cycles? Why not, Anurag? Uh, yeah, I mean, the reasoning is the same. If there is a cycle, then you go 2 steps. The third step, you get a different thing from the second step. So there can't be any cycles. So there can't be any paths of length greater than or equal to 3, and there can't be any cycles. So if you remove these self loops, all that is left is a bunch of trees, right? Do people know what trees are? You must have done it in the graph theory lectures. If you don't know, that's fine. This is just the first problem.
Oh,
And
yes, I don't know.
sorry,
Can you like give the definition of it?
so do you have any idea about trees, or uh, you are completely new to it?
Like I forgot.
Okay, so tree is basically a graph with no cycles. Like this, this is a tree. Whereas this is not a tree. I mean, sure, this is this doesn't have a directed cycle, but there exists 3 edges between 3 vertices. You get what I mean, right?
Yes, yes.
Okay, so those are what trees are. So if you remove these self loops, then what you get is a bunch of trees. So something like this is 1, this may be going to 2, this may be going to 3, 3 may have a vertex coming from 4, 5. Let me draw this with purple. Maybe alone. And this is a valid function, and it satisfies the problem condition. 3 also has a vertex going to itself. So now what do we do of these these purple loops. We can just define a new vertex. So let's call this home, and if like, this is 3, this is 5, this is 2, this is 1, this is 4. So now we connect all purple loops to this home rather than keeping them as root. And it is understood if a vertex is connected to home, it means it goes back to itself in the function. So it's a fixed point of the function. So now we have a tree. Can you see we have a tree?
Yes.
Okay. Because earlier we had like a collection of trees with each tree having a root sort of, and we connect each of them, each of the roots to a new vertex that forms a connected tree. I mean, the trees are not disjoint now. And there is something known as Cayley's formula. The number of directed trees with uh, labeled vertices. Labeled vertices. N labeled vertices is n to the n minus 2. We can see this if n is 2, there are two vertices, 1 and 2, and we have two options, either go from 1 to 2 or we go from 2 to 1, which is equal to 2 to the might have gone wrong here. Oh, sorry. That's for undirected trees. For directed trees, number of undirected trees with n labeled vertices is this. And for directed trees, n labeled vertices
Is it like 2 to the n minus 1, that thing? Number of
like
undirected
whole
trays. Okay.
so that is unlabeled vertices, I guess. My bad. Oh, I'm clearly sorry, guys. I did this problem a long time ago. I'll have to search up the theorem. Yeah, so it is n to the n minus 2.
Directed or undirected?
Directed. And we have the vertices 1, 2, 3, 4, 5, and home. We have 6 vertices. And this gives us 6 to the 4 equals 1296 graphs. But notice that there would be some graphs which would not work because of the path condition. Every path has length at most 2. So paths with length 3 won't work. And this goes to home. This is suppose V1, V2, V3, V4. So graphs containing this type of long chain wouldn't work. We can characterize these graphs as 5 cases, right? The fifth vertex going to the home, fifth vertex going to V1, fifth vertex going to V2, and the fifth vertex going to V3. And the last case, fifth vertex going to V4. I'll mark this case with the green pen. You'll see why.
In any of the cases, it's still a tree.
Yeah, but the length of the path
Mm.
from V4, F of V4 is V2, and F of 3Fs reaches V1, and V1 and V2 are not the same. So this doesn't work. And the type of these graphs is 5. I mean, I've broken these graphs into 5 cases. That V5 goes to home, goes to V1, goes to V2, goes to V3, and goes to V4. In all the black cases, we have 5 factorial options that map 1, 2, 3, 4, 5 to V1 to Vi. This can be done in 5 factorial ways. There are 4 options, so we multiply by 4. But in the green case, do you notice that if we swap V4 and V5, our result would be the same? So counting 3, 2, 5, 1, and 4 goes to 2, or counting 4, 2, 5, 1, and 3 goes to 2. They are precisely the same graph. So the green case forces us to divide by 2. And these are the cases we have to subtract from 1 to 96. So this becomes 4 into 120, 480, and this becomes 60. 480 plus 60, 540. And we subtract 540 from 1 to 96, get 756. That's our answer. Did people get this? And the thing about the Cayley graphs, what I was missing was number of rooted directed trees. That's the keyword because the home is the root here. All right. So it's not as if V1 is the root and home is going to V1. Every vertex has a chain which always ends in home. So home is the root. So the number of rooted directed trees with n labeled vertices is n to the n minus 2. Like for n equals 2, suppose this is the root, the other vertex can only go to the root. For n equals 3, suppose this is the root, and we have two other vertices, 1 and 2. Suppose either both of them go to the root or they have a chain in which either 1 can appear first or 2 can appear first. So we have three cases, which is 3 to the 1. Here we have one case, which is 2 to the 0, and so on. Please tell me if you guys are stuck somewhere. I'll repeat that. Shall I move on? Or what? Please respond, people.
Yes.
Okay, so is this clear? I mean, this
Yes.
is quite theory heavy for the first problem, but I assure you, the intended solution was to bash this out with some, I guess, some casework, notice some optimizations along the way, but I just found this solution pretty, so thought it would be nice to share this with you. Okay, so the next problem. So this is saying A and B are two sets which are disjoint. They don't have any common numbers belonging to them. A and B are positive. So for every number in this list, n belongs to A or B, then n plus A belongs to A, or n minus B belongs to B. Did people have time to try this problem?
Yeah. Oh, sorry, I thought you meant will you try the problems now?
Sorry, I couldn't get you.
Just never mind.
Your microphone volume is a bit too low. You can write in the chat. Okay, no problem. If you guys have some first thoughts, some approaches, or if you solve the problem and you haven't seen it before, do tell.
Does the
Okay,
converse solve?
sorry,
Does the converse solve?
does the converse? Ah, the converse of this statement would be if A cardinality of A is equal to B cardinality of B, then
No, 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 no. The converse of the second statement.
oh no, it is written then. Nowhere is it written that if I plus A belongs to A, then I has to belong to some digit, some uh, one of the sets A or B. I mean, no, the converse doesn't hold. The statement is in one direction only. Even if you haven't tried this problem, no worries. Suppose these are
So
the
if we
numbers.
start with a positive integer I, then the next term would be I plus A or I minus B.
If we start with a positive integer I, what would be I minus A or I plus A or I minus B?
Like f of I.
Okay, so you define f of I to be I plus A or I minus B, whichever is in A union B. Is this right?
Yes.
Yeah, so you're basically drawing an arrow from a number to the next one. I plus A, then in A, I minus B, then in B. But what if you have both the numbers? You have I plus A in A and I minus B in B. What do you do then?
It's written either, like there would be only one of them.
Ah, okay. I mean, the problem holds true with if either or is written, if both are also in A and B, but I guess that works. Okay. So yeah, continue.
Give me a minute to think.
Sure, sure. You guys think on this. I'll continue at 7:35. Just collect all the ideas and we'll discuss in 5 minutes. Also, till what time do I have? The host, whoever is there.
8:30, I guess.
8:30. Okay.
Hello.
Hi.
So I guess I have some idea.
Let the other people think. We'll discuss
Okay.
at 7:35.
Mhm.
Okay. So tell me, someone was saying earlier.
Like considering a directed graph product and directed graph approach,
Mhm.
like the elements of A would be A1, A2, dot dot dot, A cardinal of A, and
Yeah.
elements of B would be B1, B2, dot dot dot, B cardinal of B.
Yeah.
So just say that there has to be some point AK in the component A such that AK maps to some another element in B, because if it doesn't, then it is an infinite cycle. It just tells that it isn't a finite set of integers.
It maps to some element in B.
Yes.
It
And
may go to some element in A.
no, like if we consider that there is no element in A, such that it doesn't match to any
Oh,
other element in B.
like that. Okay.
Yes, yes.
Suppose some element here goes to B.
No, no,
Okay.
no. I'm saying like no, if we have no
There's a
elements in B.
cycle.
Yes. No, no. Wait, no. Like the end vertex should be connected to some another vertex in B,
Okay.
and the
So,
end vertex of B would be connected to another vertex of A.
okay.
Because
So,
like if it maps to another larger element in its own, then it would be like it has to work for A. A will go to some element in B, A cardinal of A, but it isn't solely for B cardinal B.
okay. Yeah. So, who was this speaking? I can get your name.
Anurag.
Anurag. Okay. Yeah, Anurag. So you mean to say we continue drawing arrows,
Yes, yes.
and then somewhere there are only finite numbers, so we have to return to this vertex. I mean, some vertex is repeated,
Yes, yes.
some vertex doesn't erase. Some vertex is repeated. Suppose this one. Because if it isn't, then we go on forever, and but there are only finite elements in A and in B. Okay, so what happens if the element which is repeated has already been visited?
It like restricts the two elements that maps to that element. If they both are in the same set, like say some AJ map to that B2 and some AK map to that B2.
So
It like,
suppose
yes, it like implies that AJ is equal to AK.
AI goes, let's not say AI, because the number may map from B to B. So let's
Yes,
just
yes.
say X and Y, they both map to the same number. Suppose BI. Then what?
Then like X is equal to Y.
Y?
Like because BI is equal to X minus B.
Exactly. So
And BI
B,
is, yes.
so BI is in B. So to reach BI, you have to subtract B. And likewise, if it was AJ instead of BI, then to reach
So like
AJ, you
both
would
of
have
X
to,
and Y have to be in the different component.
yeah. So if it were AJ instead of BI, you would have to add A to X and Y. And this, both these cases just imply X equals Y. So a vertex can't receive two arrows. Is that fine?
Yes.
Okay. A vertex can't receive two arrows. So whenever this thing wants to end, it ends back in the original, the starting vertex. So what we have is a bunch of like, going around here, then in this, back here, in this, and just moving back and forth until we land at the original vertex. So what we have is a cycle. In which if the element we are going to is in A, is a member of A, we add A, and if the element we are going to is a member of B, we subtract B. Minus B, minus B. This. So do people get this? How I made this cycle from this mess?
Yes, yes. Yes.
Okay. So, and it may happen that this is A, this is B. We go here, here, here. And there are maybe a few other numbers, and they get missed. So what do we do now?
So now if to prove that they are distant.
Better still, we just remove these three vertices. We just neglect these three vertices because we know each one of them receives an arrow. That's a cycle, right? Each one of them receives an arrow, and they can't receive another arrow, as we've established here. Every vertex can only receive at most one arrow. Every number can only receive at most one arrow. So if we just remove them, our graph, our arrowed version would be affected. Clear?
Like the other thing would also have a cycle. We are like a bunch of cycles.
Yeah, exactly. So one cycle here. One cycle here. This is the first cycle. This is the second cycle. The third cycle. the fourth cycle, and so on until we exhaust all the numbers. Suppose the kth cycle. And in all these cycles, as I drew before, we either add A in each edge or subtract B.
It's like a linear Diophantine equation.
Yeah.
So
So
the number added would be equal to the number subtracted.
exactly, because we start, take any vertex, we add A 1, 2, 1, 2, 3, 3 times, and we subtract B 1, 2, 3, 4, 5 times. So, and we end at the same, the squared number. So 3A minus 5B must be equal to 0. All right. And what is 3 here? 3 is the cardinality of A in this cycle. Suppose the ith cycle. Cardinality of the elements of A in the ith cycle times A equals to the, minus the cardinality of elements in B in the ith cycle times B equals 0. So we can just equal these two.
Note that we can just like add them all and get the end
Precisely.
result.
Precisely. And we can sum over I. And we take A common, and we have A1 plus A2, so on till AK. AK times A equals to the same thing for B times B. And these brackets, these big brackets, are nothing but the cardinalities of A and the cardinalities of B. Was this okay? Did people follow along?
Can you repeat that? How the initial and the final point will be same?
Okay, so consider this as alpha. What's this? This
Alpha
thing?
plus A,
Alpha plus A. Alpha plus
2A.
2A. This thing? Alpha plus 2A
Alpha
minus B. Alpha plus 2A minus 2B. Alpha plus 3A minus 2B. 3A minus 4B. 3A minus 5B. 3A minus 6B, I guess. So it's 6A. Oh no, I messed up somewhere. Minus B, minus B, minus 2B, alpha plus 3A minus 2B, alpha plus 3A minus 3B, alpha minus 3A plus 3A, sorry, minus 4B. And in the last, we have alpha plus 3A minus 5B. But this was equal to alpha, right?
That's what I was asking, that how the initial and the final point was equal.
So, I mean, that's how we defined a cycle.
Like
This
he's asking
is the
how
same
there
number.
exists a cycle. He's asking this.
I'll have to repeat the problem. Okay. So what we have done is, have you understood the approach? What we have done?
Yes,
How we have
yes,
drawn arrows, and
yes.
are you comfortable with the reasoning that there would be cycle? There would be a cycle.
Yes, yes. The A and B are finite sets, so there will be a cycle.
So suppose small a is 2 and small b is 1. Maybe no. The opposite. Small a is 1 and small b is 2. Then suppose this is 5. This thing It's 5. Then what's this thing?
5 plus 1.
5 plus 1. 5 plus a.
Yes.
Okay. And then what's this thing?
5 plus a minus b.
5 plus a minus b. Then what's this thing?
5 plus 2a minus b.
5 plus 2a minus b. But now, in terms of numbers, what's this? 6. We add 1 while going to a. We subtract 2 while going to b. So this is 4. We add 1 again while going to a. And this is 5. So if there is a cycle, the cycle is nothing but what? A sequence of operations. We have defined a cycle as a sequence of operations. I mean, what's the next operation after reaching this number? Either it's I plus a or I minus b. So in either case, this can be I plus a or I minus b. This is what we've defined. F of I equals I plus a or I minus b.
Yes.
So this can be I plus a or I minus b. This can similarly be whatever this thing is. Suppose j plus a or j minus b. This thing right here.
Yes.
And we continue along. So in the end, we get I plus some times of a times something minus some times of b. And if we follow a path, I mean, if we follow a bunch of arrows, we add some a's and we subtract a few b's. What it means to get back to our original number is we add a bunch of a's, subtract a bunch of b's, and we get the same number. I mean, that's how a cycle is defined. Do you get this?
Yes.
So is this thing now clear? Alpha plus a,
Yes.
alpha plus 2a, alpha plus 2a minus b, alpha plus 3. So all sorted? All set? Okay.
Yes.
Any further queries? Okay, nice. So we'll move on to the third problem. Okay, so did you guys try this problem or should I give some time? And we're short on time,
Sometime.
so sure. So let's uh, let's wait till 5-6 minutes.
I think the main thing is here to consider modern and then get a bunch of get some graphs.
We'll see. You can tell after a few minutes. Okay, so shoot. What are your ideas?
Like, we consider modern for any index I. So we start from an index AI.
First, no, uh, the proof will come at the end. First, tell me what is your guess? I mean, if what is
I
your
guess
answer?
I guess no integers work.
Sorry?
Sorry, but I am not sure if no integers work.
Okay, no integers work. I mean, I, I said I couldn't hear what you said. So no integers work. Ah, have you tried this for small values?
No. Like I have like after some kind of value, it just stops working.
For n equals 2, I think it works.
No, for
Because
like n equals to we are like 2 doesn't divide 7 plus 2, which implies 7 and a2 are of different parity. But we consider the index to be 1 and 2, then it implies that a1 and a2 are of the same parity, which is like in contradiction.
mm, I think you are misreading the problem. The problem says, suppose we are given n integers in a circle, a1, a2, ai, an. Does does there exist a starting point such that the partial sums from ai that is
Oh,
AI,
okay.
AI plus the next term, AI plus the next 3 terms, AI plus so on till AI summed up till AI minus 1, in completing the whole circle. In these n numbers, can AI be chosen such that none of these n numbers uh, have a number divisible by
I
n?
misread it as like for every I between one and.
And no problem, no problem. Yeah, a rule. So, can you speak or you
Yes, I
would?
can.
Okay, sure. Yeah, you got it works for 2 and 3. So, what do you conjecture then?
Yes. I guess it will be true for all integers n, but I'm not 100% sure.
For all integers. Okay.
I don't see any reason it won't work for some, especially given 2 and 3 of opposite parities.
I guess it doesn't work for some integers. Can I just like try to give a formal proof?
Sure.
An idea which I have. Like, say there exists some such AI in a circle.
Okay.
Okay. So consider those indexes to be modern. So exactly to we like map to AI, then we map to from AI to AI plus one, AI plus AI plus one modern. So we will have like
Sorry. AI, then AI
like
plus 1.
like I'm mapping modern. Like we start from AI,
Yeah.
then we map to AI plus AI plus one modern.
No, how can you be sure that it will map to AI plus 1
No, no,
modern?
AI plus AI plus one.
Okay. Oh,
Yes, yes,
that thing.
yes.
Yeah.
Okay.
Okay.
Yeah. Like some AI maps to this, and then
Yeah.
some it maps to some AI plus two, and so on. So we have like there are n elements in this graph, and we can have like exactly n minus one modern, because like if any one of them is zero modern, then it would be a contradiction
Yeah.
if it were.
So, okay.
Yes. So like we will have something AJ mapping to some AK modern. So like we have some two numbers are congruent in this. So we just
No.
okay.
2 numbers are not congruent. What you mean is, was it go uh, one collection of numbers goes till AJ and another collection of numbers goes till AK. So what you mean is the numbers from AJ, suppose these two are congruent, mod n.
Yes.
What you mean is AJ plus 1, so on till AK minus 1 plus AK. This is
Yes.
congruent to 0 mod n.
Yes. Yes.
Yeah, so AJ is not congruent to AK. Yeah, sure.
Wait. This was like assume the proof for uh, that thing that it works for all life. So it was like in counter proof for that. But I don't think there will be an obstruction in their existence.
Okay, no problem. Arul, if I'm pronouncing your name right, sir.
It's Arul.
Arul. Okay, sorry. So Arul, does
Yes.
this clear that all integers don't work?
Okay.
Because you start at 0, you you start anywhere, you're going to get 2 2s at least, and that's going to be 0 mod 4. Uh, can you generalize this construction which I've made and see which end don't work?
So like for any n, we will have some string of consecutive integers. consecutive indexes such that their sum is 0 modulo n. So only
Yeah,
we
yeah.
can
You,
reach
you
this thing.
you leave the proof. For now, you leave the proof. You
Okay.
just focus on the construction first, because that will give you some insight on which numbers to attack, which numbers to go for. Proving for all integers when clearly some work and some don't is fruitless, right? Think about how I'm making this construction.
All primes p, I think.
Okay, all primes. So why do composites fail, in your opinion?
Because if we can express it as PQ, we could take the circle 0 and replace the rest with Qs.
Exactly. So rest of the Qs, rest all numbers are Qs, and this works. Why? Because
Because the sum is PQ square minus Q, which is not divisible by PQ, and somewhere in between we'll get PQ as a sum, irrespective of where you start.
yeah. So there are n minus one Qs, and n minus one is definitely greater than P, which is n by Q. N by Q. So we'll have a consecutive set of PQs, at least PQs, right? And the sum, as Arul pointed out, is not divisible by n. It's PQ minus 1 times Q. Yeah. And PQ does not divide this. Or PQ may divide this, but if we choose P and Q to be co-prime, then PQ does not divide this. Anyways, PQ doesn't divide this. Sorry, I'm going crazy. So, do people see why this construction works?
Yes.
Like I'll show just another case. If n equals, suppose, 10, then taking all these as 2's, 5 2's, 1, 2, 3, 4. This works because the sum of 2's is 14, not divisible by n. 14, sorry, 18, not divisible by 10. And we start at 0, we get 5 2's here. If we start at this 2, we get 5 2's here. We start at the next 2, we get 5 2's, and so on. In any case, we get 5 2's. So all composites fail. And this thing proves that. And all we're left is to check if primes satisfy this condition or not, which is kind of easier because you're just one divisor to worry about rather than all the prime divisors and their powers in a number, in a composite number. So, and 2 and 3 satisfy this. So, I mean, and primes are nice. So it may be a good guess to assume that all primes do satisfy this, and just check. I mean, just try going to prove that all primes satisfy this. And if we can't prove something, we figure out and go back and see which primes fail, if any do. So how would you go about showing that all primes work? Like, suppose we're given a circle of numbers and replace n by p from here on. So the objective is to show that there exists an index such that this thing plus its first neighbor, this thing plus its first two neighbors, plus its first three neighbors, and so on, till this thing plus all of the other things. Some
Just note that like if it works for everything, then it implies that P, like we have, for the sake of contradiction, assume that we don't have such a string of consecutive indexes.
we don't have such a, okay, so assume such an a such an a doesn't exist. A j, I should say, such an
Yes.
aj doesn't exist. Okay.
Yes, yes.
And-
So
and
like you try
note
to,
one second, just a second. Note that this is a powerful claim. I mean, just assuming contradiction, assuming to go, just going for the proof by contradiction gives you a very strong hand, because now you've reason to assume that starting at any AI, you have a string of consecutive numbers which sum to 0.
yes, yes, we do.
So for A1, suppose A1 till A5 is 0. For A2 till AP minus 3 is 0. A3, suppose till A20 is 0. And for every such starting point, you have something which eventually adds up to 0, mod B. And this is a strong grip.
Yes, yes, it is.
Yeah, continue, Anurag.
So like we have that string for every number. So we like try to conjugate, means like we just subtract that from that original sum, a1 plus a2 dot 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 an. That thing that is like if we have some string of consecutive such indexes, so we try to exclude those from the circle and take those that take those consecutive indexes that isn't in that zero mod p thing. We have that.
Sorry,
Yes,
I couldn't follow along. Sorry,
like
can you repeat it?
say a1 plus a2 plus dot 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 a5 is congruent to zero mod p.
Sure.
So like now we take AP plus AP minus 1 dot 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 AP minus 1 till A5. We consider
Yeah.
the strings here. So like
Okay.
again, if we have such string in AP, so we go to from AP to some AP minus K, AP minus AK, AP minus K, and then we do the same with
Okay.
that
Okay.
P minus K, and we keep doing that.
Oh,
So
one thing. Sorry to interrupt, but
yes.
we may not have the last number as AP in all the cases. If we start at A3,
No, like consider any index, no, because it is circle, so it doesn't matter. Like if
so
yes,
then we'll start at A2 from the other side. Yeah, okay.
yes. So now we start to A2, then we get that if we do have such a string also there, so you get that A2 plus dot 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 some AK is congruent to zero mod P.
Not congruent to 0 mod P.
Yes,
Congruent to the sum of all numbers mod P.
yes, yes. So
Okay.
like if we do have such a string for A2 such that this A2 now we take like this is AI plus 1. So like we go from AI, we know that there is an consecutive index sum such that AI plus some dot 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 AK is congruent to zero mod P. Note that this can't like go forever. If it goes forever, then we will have that whole sum is divisible by P, which is in contradiction.
So you don't need these arrows from behind. Right? You can just use the forward ones, to conclude that the whole sum is divisible by P somehow.
Yes, yes. So we get a contradiction and we are done.
Yeah. My solution also goes along the same lines, and I think our role is also just about. Arrow has also reached that point. So this lecture is arrows. So obviously we haven't used arrows in this problem yet, and this is the last part. So it's a strong hint. Suppose we start at A1 and it goes on till A5. Okay, we know that A1 plus so on dot 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 A5 is 0 mod P. What do we do now? We start at the next vertex. Here, A6, we continue. Suppose it stops at f of A6. We start at f of A6 plus 1. Suppose it reaches this vertex. We start at the next vertex. Note that this thing has to reach the starting point. How should I say it? A vertex behind the starting point of some arrow, right? Let me draw concrete objects. So suppose this is one arrow. The second arrow starts from here. It goes on till here. This is not what we want. This ended at the place where an arrow began. We want to end it one vertex before an arrow began. So we start here. Suppose we go until this vertex. And now suppose we go until this vertex. Now we have no option except to stop here. One place ahead of which this arrow begins, or we stop. Or we stop. Let me label these vertices. So starting at 4, we're already done, right? Because we went from 1 to 2, we went from 2 to 4, we went from 4 to 1, we went I'm just sorry, 2 to 4, then from 5 to 3, but 3 is before 4. This thing is before 4. So starting at 4, we have 4 to 1, then 2 to 4, then 5 to 3. So what we have is 4 to 1, 2 to 4, then 5 to 3. So in effect, we have completed 2 rounds of the circle. Is this clear? I might be confusing people. Might be easier with arrows. Okay, let's go with arrows. So start at any vertex AI and draw an arrow from AI to AJ. If AI plus 1 plus so on plus AJ minus 1 is congruent to 0 mod P. We know that there exists a consecutive string starting with AI which is congruent to 0 mod P because we assumed we were going for the proof by contradiction, right? Is this clear? That how am I defining an arrow?
Yes.
Okay. To everybody, because speak up now or
Yes.
Like
I'll
consider
just
the
move
minimal
on.
ages such that this sum is 0 mod P. It would help considering the
Yeah,
minimal
yeah,
ages.
yeah. I mean, that's okay. Yeah, that will help in the bounding that's about to come. So assume that j minus I is less than equal to p. Okay. Because, okay. And consider indices mod p. So j can be I plus p. If we complete the whole circle. So assume this. And okay. So we draw an arrow from AI to AJ. And then we continue. So the main theme of this lecture seems to be you just draw an arrow, you end, you draw another arrow, you end, you draw another arrow, and just see what happens. See what happens to the structure. So you draw an arrow here, you draw some arrow here, you go on, and eventually you'll go back to some vertex you've already visited. That may be AI, that may not be AI, but you'll go back to some vertex you've already visited. All right.
Yes.
Okay. So what this means is that
Like that sum that was congruent to the sum of all elements mod p will be congruent to 0 mod p, which is like in contradiction.
yeah, but how are you handling if all the elements of the cycle, all the elements a1 till an are not covered? Like if this element maps to some element which was already in the cycle, already in the
So
path,
like
I
note that AI till AJ was 0 mod, that thing,
yeah,
okay? So
yeah,
like
okay,
now the vertex that we ended from, say
yeah, this
AM,
one
yes, it's
am,
AM. So like
okay,
till this to AN, we have like this thing is congruent to the sum mod P, this total sum of uh, all elements mod P, which is not congruent to 0 mod P. And we have like AI till age is congruent to 0 mod P, which is like in contradiction then. Because
sorry,
we
what is an here? I mean, I've not drawn
AM.
an in the picture.
So like we have that AM to AI plus 1 is not congruent to 0 mod P, because that thing is congruent to the total sum mod P. AI minus
Yeah.
1. Yes. And we have like AI plus till AJ is congruent to 0 mod P. So if this thing AM maps to AJ, it implies that the sum is congruent to 0 mod P, which is like in contradiction. Did you got my point? Hello.
Sorry, can you explain with an example? Suppose a1 goes,
Like I couldn't explain it example. Wait, I will just try to send a kind of photo. Wait, can I be allowed to share this thing for some time so I can show how it works?
uh, you can just tell me. I mean, it would be clumsy to
Like we
just
have that
go back and
if we
forth.
sum from AI to AM, we have that this thing is congruent to 0 mod P.
One second,
AM.
just let me draw the diagram again.
Okay, okay. Yes.
Some arrows, and then we go back, we go to AM,
We
but
have that,
this doesn't
yes,
go to AI, this goes to AJ. Yeah,
yes.
continue, and we
So
have some
we have
elements
that,
in between.
yes, yes. We have that this sum AI to AM is congruent to 0 mod M, AI to AM.
Yeah.
So like the rest of the elements would be congruent to the total sum mod P.
Hmm.
So if the rest of the elements are congruent to the total sum mod P, so it implies that their sum is not divisible by P.
Hmm.
So now we like sum from AM to AJ. So we go from AM to A minus 1. We have that AM to A minus 1 isn't congruent 0 mod P. But we had like AI to AJ is congruent to 0 mod P. So like if the total sum from AM to AJ is congruent 0 mod P, the sum of rest elements would be also congruent to
Yeah,
0
exactly,
mod P.
exactly.
Yes,
So
yes.
uh, this was pretty obvious. Just drawing a straight arrow makes things confusing. You are essentially going from AM to AJ, and you just neglect the arrow from AI to AJ. So what you have is AJ arrows to AM and then another one to AJ. And this can also happen. You can also go around the circle many times. So suppose we start at AJ, and this ends here, and we go again. This ends here. So, and this finally goes to AJ. So we may have many such loops uh, around the circle. Now that inequality which I was just talking about, that j minus I less than equal to p will come into the picture. We want to show that there are at most p minus 1 revolutions of this circle, because if there are p, then that sum. So what's the sum of all these numbers? The number of revolutions times a1 plus so on till ap. Is this fine? Because we're going from aj plus 1, so on, going till aj minus 1, then going again, going again, and finally ending at aj minus 1. So we essentially do rounds of the circle and visit each AI exactly the same number of times. Is this fine?
Yes.
And so if we complete 2 revolutions, suppose we stop here and now we stop here, then every number is covered twice. If we do 1 revolution, every number is covered once. So the sum of all numbers, the sum of all such consecutive strings, the numbers in all such consecutive strings is the number of revolutions times the sum of all numbers, which we know is 0 mod p.
Yes.
But this thing is not 0 mod p. So we have that the revolutions, number of revolutions is congruent to 0 mod p. But now notice that there are at most p revolutions. So because each revolution can have has a unique starting point. If we reach the same starting point again, then we have a cycle and we're done. So each revolution has each consecutive strings has, sorry, p consecutive strings. My bad. At most p consecutive strings.
Like every number is
P arrows.
is
Sorry,
repeated p times at most.
we have at most p arrows because there are p numbers. There can at most be p arrows, and each arrow contains at most p minus 1 numbers, because it can contain p numbers, because then we would rotate about the whole circle. And each arrow has at most p minus 1 numbers. Is this fine?
Yes.
Yes.
Other people?
Yes.
Okay. So all arrows, this is getting quite crowded. All arrows have at most p times p minus 1 numbers, which is equal to p times the number of revolutions. Because in one revolutions, I mean, the left hand side, this thing is equal to p times the number of revolutions, because each revolution has p numbers. Is this okay?
Yes.
So we get that the number of revolutions is less than equal to p minus 1, which is a contradiction. So let me just recap what we did in the proof for p's, for primes, all primes. We assumed for contradiction that there doesn't exist such an AI says that all consecutive strings starting from AI are not divisible by p. So what we have is the condition that for all starting points, we have a consecutive string that is divisible by p. And for the smallest such string, we draw an arrow. Okay, we draw an arrow from AI to AJ if AI plus 1 plus so on till AJ is divisible by p. And now we follow the arrows. If AI goes to AJ, AJ goes to some other thing, goes to some other thing. And at some point, we return to a number which was previously visited. If we return to this number, we just neglect all of the arrows behind it. And because this thing just means all of these numbers too. So we have all the numbers in a finite number of arrows starting and ending at the same point. Now we have p arrows, at most p arrows, because there are at most p numbers. Each arrow has at most p minus 1 numbers, because no arrow can span the whole circle, as the whole circle is not divisible by p. So all arrows have p into p minus 1 numbers, which is because the arrows start and end at the same point. All the numbers are visited the same number of times, which is the number of revolutions. All arrows combined have p times the number of revolutions numbers, which is less than equal to p into p minus 1. So we have the number of revolutions less than equal to p minus 1. But also, all the numbers, the sum of all numbers. The sum of all numbers is the number of revolutions, which is the number of times each AI has occurred, times A1 plus A2, so on till AP. This thing, A1 plus dot 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 plus AP, was given to us as not divisible by P. So it vanishes, and we have that the number of revolutions is divisible by P. These two conditions give a contradiction simultaneously. Is this proof fine?
Yes.
Yes.
Any doubts you can ask me now. We are about to end. I assume everyone is fine. So cool. We could discuss 3 problems, and you have the rest of the 7 months to try for yourself. Do write in the arrows channel if you have any doubts or want some help. And yeah, bye bye. Thanks for joining.
Bye. Thank you.
Class.